This is a video for the evaluation of source artifact. This video contains 4 parts. First, we introduce SOAR and our real-world testbed for the evaluation in the paper briefly. SOAR is the first end-to-end SRI system specifically designed to support autonomous driving systems. It consists of both software and hardware components carefully designed to overcome various system and physical challenges. SOAR can leverage the existing operational infrastructure like street lampposts for a lower barrier of adoption. It adopts a new communication architecture that comprises a bidirectional multi-hop I2I network and a novel passive I2V broadcast service, which are designed based on off-the-shelf 802.11 AC interfaces in an integrated manner. SOAR also features a hierarchical DL task management framework to achieve desirable load balancing among nodes and enable them to collaborate efficiently to run multiple data-intensive autonomous driving applications. We deployed 18 SOAR nodes on existing lampposts and 3 servers in buildings as cluster heads on our campus. The 2 clusters cover 0.3 kilometers and 0.5 kilometers of road, respectively, and have been operational for over 2 years. The evaluation in our paper is conducted in the real world based on our deployed system and a test vehicle. The SOAR nodes comprise a series of hardware components, including multimodal sensors, antenna, communication units, and computing units. The hardware setup has been described in our published artifact. In this video, we demo the functions of 3 key modules in the SOAR system. They are the I2V broadcast communication, the cluster-level task dispatching among SOAR nodes, and the task scheduling during local execution. For better visualization, we implement and show them on an indoor test bed with the same hardware setup as the real SOAR nodes. Firstly, we demo our artifact of the I2V broadcast module. We use a TX2 and a PC to simulate a SOAR node as the transmitter and a vehicle as the receiver, respectively. Both of them are connected to a Wi-Fi adapter. The hardware setup of this testbed is the same as we used in our real-world experiments on roads. On both the transmitter and the receiver side, we should install our modified RTL8814A Wi-Fi driver. The modified driver and the installation guide can be found in the 8814A folder. Then, we can install the transmitter and receiver with CMake. In real-world operations on multiple SOAR nodes, we need to prepare the channel configuration for each node. We should run the GPS.py on the receiver side to switch the channel to receive data from the different SOAR nodes according to the location. Here, we show the demo of the function of the transmitter and the receiver. We SSH into the TX2 that is connected to a Wi-Fi adapter as the transmitter. First, we turn on the monitor mode with the script and set the channel. Then we can find that our Wi-Fi adapter is operating in monitor mode. Lastly, we run the transmitter demo with arguments that set the transmission scheme, data rate, and MCS. We can see that the transmitter has now started broadcasting data at around 30 megabits per second into the channel we set. Similarly, on the receiver side, we first run the script to turn on the monitor mode. We then run the receiver with arguments that set the receiving scheme, Wi-Fi interface, output path, and whether to save the received data. We can see that the receiver now receives the data by sniffing the packets in the channel. After stopping receiving, we get two files. A data file that saves the data we receive. Another file is named result.csv, which is a data trace that logs the information of each packet we receive. We use this file to calculate the evaluation metrics in the paper. We uploaded some of our data traces, which can be used to plot our result figures in the paper. For example, the result of the performance under different vehicle numbers. And the performance comparison between with and without network coding. Next, we demo our artifact of the cluster-level task dispatching. In the computing folder, we provide the artifact of source task management framework, including the cluster-level task dispatching executed on the cluster head and the local scheduling during the task execution on each SOAR node. Here we show the workflow script of the environment setup and the commands of operation on the SOAR nodes we deployed on campus. For better visualization, we validate our artifact of cluster-level task dispatching with a quick demo. Firstly, in the demo.py, we set the number of nodes in the cluster and the sensors on each node. We can set the task by adding config files in the config folder. The config file contains the information and parameters of the task. Then, here we manually set the bandwidth between each pair of SOAR nodes in the cluster. Note that in real-world experiments, each node periodically measures the I2I bandwidth to others and updates it to the server to maintain the bandwidth map. Lastly, we run the demo.py. The output is the dispatching result of the tasks among the SOAR nodes. For example, the LiDAR detection task 030104 originally on node 3 is now dispatched to node 2 for execution. This shows how we get the result in table 3 in our paper. The result here is different from that in the paper because the bandwidth map is truly measured in our real-world experiments. Lastly, we demo our artifact of the local task scheduling. For the local task scheduling, similarly, we published the completed codes that ran on our deployed SOAR nodes, and we provided a quick demo to validate our artifact. Firstly, we set the configuration of tasks to be executed on a node. For example, recall that after the cluster-level task dispatching, there are two tasks that need to be executed on node 1. Therefore, we write the configure file of node 1 in the config folder to set the task type, data shift time, deadline, and execution time. Lastly, we can run the local_demo.py with arguments that set the node ID, method, and execution time. For example, we ran source method for 1000 milliseconds. Then, we can get a log file that records the execution trace of each task, including the model it uses and the execution time. In our experiments, we leveraged the log files on the SOAR nodes to evaluate the metrics and plot the result figures in the paper.